So I am obviously well aware that you all had some exposure to op-amp circuits back in engineering 221. I'm going to politely request that you forget literally everything about op-amps that you learned in that class because that class is a general purpose class for all engineering students. We vastly oversimplified how they actually work and behave. And we were limited to only dealing with negative feedback op-amp circuits. In this class, we're going to go into much greater detail about how op-amp circuits worked, their applications in not only negative feedback configurations like we did in circuits 1, but also open loop and positive feedback configurations, okay? So we are going to start under the assumption that essentially you know nothing about what amplification is. So let's say, very generally, that I have a signal. And this is going to be some time varying signal because amplifying DC signals, while it does have their uses, is probably the most boring application of amplification we could think of. So let's say that we have just a simple time varying signal that is some form of, let's just say sinusoidal oscillation right now, just so that I can reasonably reproduce it. And this signal right here would be our input signal. So I'm going to say that this would be maybe Vn of t or possibly In of t, because we can also amplify currents. And we were trying to generate an output signal, which is going to be this guy over here. And we wanted our output to essentially be a scaled version of our input signal. So something akin to this kind of loosely, right? Where this would be V out as a function of time or I out as a function of time, so forth. So in order for us to essentially be able to scale some time varying input signal, we really have two options, okay? So our first option is some form of amplification. So over here on the left-hand side, I'm going to put amplifiers. And the other option would be to utilize what's called a transformer. So a transformer can be used to boost signals as well. And as it turns out, actually, transformers are going to be the first topic that you learn about in Circuits 3 next fall, okay? So these two methods of scaling signals work in vastly different ways and are used in vastly different applications. So I want to try to explain kind of what's the difference between those two so that we have an understanding of why we might want to use one version for scaling signals versus another, okay? So the first thing that we should realize about an amplifier specifically is that amplifiers are active devices, meaning that they require external power, okay? So all amplifiers boost signal levels by adding some additional external power to the signal. That's what's effectively making it larger, okay? On the flip side of things, a transformer is an example of a passive device, Now, I briefly talked about the difference between active and passive devices in my Engineering 221 section, but I don't know what everybody's exposure is to it. So a passive device is the descriptor that we usually use to talk about things like resistors and capacitors and inductors, where they exhibit those specific behaviors without requiring any sort of external stimulus, okay? So a transformer is a device that is able to convert or amplify or scale voltage and current signals without the use of external power, okay? So that use of external power or not having access to external power brings us to the second main difference between an amplifier and a transformer. So in an amplifier, the output power of our signal does not necessarily have to be equal to the input power. In fact, it will often be greater than the input signal. So if our input signal is delivering, let's say, 5 milliwatts, our output could be generating as much as 5 watts, depending on what type of load we have, how much signal we boosted, all of that kind of good stuff. That's the type of amplification that we all experience every time we listen to a stereo or anything like that, right? The actual audio signal doesn't have the strength to move the physical mass of a speaker around. So we have to use what's called a power amplifier to give our system enough power to actually move that magnet. Well, in a transformer, the output power will always be less than or equal to the input power because it is a passive device. In an ideal transformer, where we don't have any kind of losses or anything like that, our output power will be exactly equal to our input power. But any real practical transformer will have losses because current's going to cause wires to heat up. It actually requires a certain amount of energy in order to magnetize the transformer's core and things like that. So we should usually see that our output power is slightly less than our input power. And that ratio of output power to input power is the efficiency at which a transformer is scaling those signals. Now, another side effect of effectively our transformers obeying what we would normally consider to be the law of conservation of energy, meaning the input signal has to, or excuse me, the input power has to be greater than or equal to the output power, is that anytime we use a transformer to scale up a voltage, it has to scale down the current in order to keep those powers balanced, right? With an amplifier, we don't have to worry about that because we're injecting external power into the system. So if we scale up the voltage, we can also scale up the current, and that's exactly how power amplification works. Okay. So the end results of amplifiers and transformers can look fairly similar, but they are very, very different in application and theory. Okay. All right. So with that out of the way, let's talk a little bit about what exactly an amplifier is. Okay. So amplifiers are electrical and, sorry, that looks shitty, circuits or devices which are used to generally increase the magnitude of the electrical signal. I'm going to put in parentheses here, V, I, or P, so voltage, current, or power, applied at its input. So we typically represent amplifiers in a couple of different ways within the field of electrical engineering. And to some extent, it kind of depends on whether we're looking at things from the standpoint of communication systems or control systems or just general basic circuit theory. So I'm going to introduce a couple of little different ways that we might see amplifiers represented. Okay? So the first thing that I'm going to do is a simple black box representation. Okay. Yes.
Is PL always not bigger than PE?
So it depends on whether, so we can use an amplifier to attenuate signals as well in some specific cases. So our output signal doesn't necessarily have to be larger than our input signal. So that's why I just put not equal to. So there's nothing explicitly stating that the output signal of an amplifier has to be greater than the input signal power. Yes, Joshua.
So in your representation, your output is greater, like I guess for that example, your output is greater than your input, like for what you drew.
So the magnitude of up here, the magnitude of that voltage or the magnitude of that current is definitely larger. The power would depend on loading and things like that. Yeah. Okay, so starting with our black box representation. Okay, so we might have something that looks akin to this, right? So I'm literally just going to have what I'm going to call a black box amplifier here in the middle. And then over here on the left-hand side, which is typically designated for inputs, I'm going to have a generic signal X of t. And then over here on the right-hand side of our black box amplifier, which is typically associated with the outputs, I'm going to have a signal Y of t, where X of t could be a voltage or a current, Y of t could also be, or actually X of t could be a voltage, a current, or a power, and Y of t could be a voltage, a current, or a power. And just for what it's worth, if I have a voltage in, I don't necessarily have to get a voltage out, and we'll talk about that here in a moment, okay? So in this case, we could think of the black box amplifier as effectively acting on some input signal and producing some output signal Y of t. So the black box amplifier circuit will have what's commonly known as a transfer function that mathematically describes how the amplifier itself acts on that input signal. All circuits realistically have transfer functions, but for an amplifier, we usually call that transfer function the gain of the amplifier, where gain has the symbol capital A, and our definition for our gain is going to be the output signal divided by, the input signal, okay? And so from this representation, we could see that our output signal Y of t would just be our gain A multiplied by our input signal X of t. Now, another way that we could represent this relationship is with what's called a signal flow diagram. For a simple open loop amplifier, because we're not worried about feedback or anything like that just yet, this is going to be a very simplistic representation, right? So a different way to represent this exact same system would be something like this. So the triangle is the general signal for an amplifier in signal flow diagrams as well as most schematic diagrams, where we would have our input signal x of t on the left-hand side, our output signal y of t on the right-hand side. You may also see little arrows indicating explicit directions for signal flow. And you would probably also see the gain of the amplifier depicted in that triangular amplifier block as well. So in this case, we would have just once again, y is equal to a times x of t. So this is our signal flow diagram representation. And this representation becomes particularly handy when we're looking at networks with feedback, and it is almost exclusively how control systems are laid out using amplifiers to do different things like proportional control, integral control, derivative-based control, and all kind of good things like that. So I'm trying to introduce some of the topics that we'll see in your later courses here so that you're kind of getting an exposure of everything that electrical engineering has to offer, other than electronics. Okay, so let's talk about different types of amplifiers real quick, okay? So there are lots and lots of different ways that amplifiers can be classified. We are going to work at the most basic level in this class, since this is your first real quote unquote electrical engineering course, okay? So what I'm going to do is I'm just going to construct a simple table here. I'm going to put input signals on the left-hand side, output signals here in the middle, and then the amplifier type or name will be over here on the right. So let's start with the one that you guys are probably all the most familiar with. So whenever we have a voltage signal as our input, and we measure a voltage signal at our output, this is hopefully fairly obviously a voltage amplifier. Okay, so voltage goes in, voltage comes out. This amplifier scaled our voltage signal. So this is a simple voltage amplifier. The most common voltage amplifier that we have probably seen would be the preamplifier stage of actually things like our car stereos and stuff like that. So think about this in context of your antenna is receiving an electrical signal that has been broadcast by a radio station, something like that, very far away, okay? So typically radio stations broadcast at pretty high signal powers. Usually for AM radio, it's actually going to be on the order of, I believe, usually hundreds of kilowatts to potentially a megawatt, depending on how far they want to broadcast their signal. As a quick tangent, the reason why AM radio stations have to broadcast at such high signal powers is because the wavelength of those radio stations is so long that the antenna lengths on our cars and stuff like that are actually very inefficient at picking up those signals. So they have to broadcast it at a really high power so that we can actually pick up enough of that signal to do anything with. FM radio stations, satellite radio stations, things like that get to broadcast at much lower signal powers because the length of our antennas are comparable to the wavelength of those signals. And so we don't lose as much of the signal power when we pick those up. Anyway, so the signal that our antenna picks up is typically on the order of just a few millivolts. The further we are from a radio station, the lower that number is going to be. Well, the preamp stage of that audio amplifier is going to effectively boost those voltages to what are called line levels that will then go into a power amplifier stage that's used to drive your speakers and things like that. So every single one of us actually has a voltage amplifier in our pocket or sitting on our desk in the case of Connor, because his phone is not in his pocket, but we all have voltage amplifiers in our phones because that's what's picking up the telephony signals. And then it's going into a power amplifier to be able to actually drive the speaker that we hear the phone call and stuff like that with. And again, any type of audio amplification is usually going to involve a voltage amplifier preamp stage and then a power amplifier secondary stage in order to drive the speakers, okay? The second type of amplifier is when we have current as our input and current as our output. And this is what's known as a current amplifier. I'd be willing to bet that there are actually several current amplifiers in our cell phones and things like that as well, because current amplifiers are generally used as what are called buffer amplifiers that are used to maintain signal strength as we do processing on those signals, okay? Then we can have an amplifier where we have voltage at our input and current at our output. This is what's known as a transconductance amplifier. Effectively, any stage of a transistor-based amplifier, or let me put this a different way. Single stage transistor amplifiers are all transconductance amplifiers because a transistor being used as an amplifier converts some input perturbation or voltage into an output current. So all transistors effectively work as transconductance amplifiers. Then we have the opposite of this configuration where we have current as an input signal and voltage as an output signal. And this is a transimpedance amplifier. Okay. Certain transistor amplifiers can be configured to work as transimpedance amplifiers. Then lastly, if we have essentially power as an input signal and power as an output signal, then we have a power amplifier. Okay. So these are the basic classifications, most simple classifications of amplifiers that we're going to be dealing with in this class. We are largely going to focus on voltage amplifier systems because they are by far the most common type of amplifier systems. And the operational amplifier itself specifically is a voltage amplifier. Okay. So let's look at a simple representation of a voltage amplifier circuit. So I'm going to start with my amplifier here in the center of the page. And I'm just going to label this guy a black box voltage amplifier. And I'm going to give this voltage amplifier a gain of A subscript V, where that subscript V is literally telling me that this is voltage amplification, okay? Now I'm just drawing my terminals for the input side. And I'm drawing my terminals for the output side, like so. So because this is a voltage amplifier, I'm going to label the input of this voltage amplifier as a voltage Vn of t. And very similarly, I'm going to call the output here a voltage V out of t. Okay. And I'm going to put some dashed red lines here. And so everything that's going on between these dashed red lines is what we're going to call the amplification stage of this system. Now I'm going to move over to the input side of things. Okay. So that's what's going to be connected to the left to the input terminals of our op amp. And this is going to be the source side of things. I'm choosing to represent this as a practical voltage source. So this could be some resistance RS in series with some signal voltage, which I'm just going to call V sig as a function of time, like so. Okay. That could just as easily be a practical current source representation of some sort of signal generator, and in which case I would have a current source in parallel with that resistor RS, much like we learned about in circuits 1. But for what we're talking about here, it doesn't really matter. We could use a practical current source to generate an input signal voltage Vn, or we can use the practical voltage source to do it like I've represented here. Either way is perfectly fine. Just want you to know the source is going to be on the left-hand side, and we are definitely going to be taking into account any internal resistance of our source that might be present as well. On the output side of things, we are going to have our load, right? So I'm just going to choose, for this particular simplistic example, to have some resistive load, R sub L, right? Quite obviously, our load doesn't necessarily have to be resistive. It could be capacitive, inductive. It might be a speaker. It might be a light bulb, any of those things. But for simplicity's sake, we'll just leave things as a resistor. And I'm going to define the voltage drop across this resistor as our load voltage at the output, V sub L of t. And then this is the load side of our system. So I want to ask you guys, essentially, what is the desired or ideal behavior of this circuit? So best case scenario, what is this circuit trying to do?
Perfectly amplify the signal produced on the source side.
Exactly right. So in the very best case scenario, our voltage signal VL of t, so the voltage drop across our load, will simply be A, just going to leave it as a generic amplification factor for right now because it's not going to be exactly AV, multiplied by our signal V sig that we applied over on the input side of things. Absolutely right. Okay. Now, What we are going to try to do here, and I know this is going to seem perhaps a little odd because it definitely is, but we are going to try to infer using Thevenin's theorem what a circuit representation of what that black box might be, okay? And so this representation that we're going to come up with is what's called the practical amplifier model. The one that we are going to be dealing with is specifically going to be a practical model for voltage amplifiers, but every voltage amplifier, regardless of how simplistic or how complex it is, can actually be characterized by this pretty simple model. Doesn't matter if it's made of 1,000 transistors, capacitors, and inductors, or if it's literally just a single transistor and 2 resistors. Either way, it's going to behave like this simplistic model, okay? So if we were to disconnect our source voltage entirely, so if the source part was completely disconnected and we looked in to those input terminals, okay, what do you think we would see, what we would see from a Thevenin context, right? So we're trying to effectively get a Thevenin equivalent circuit. So if we have no voltage source connected because we've turned it off and we look into the terminals, what are we finding? So we would find a Thevenin voltage of potentially 0 volts or something like that. So what I'm trying to lead you towards is all we would see would be some resistance, right? So our Thevenin equivalent circuit should be a voltage source in series with a resistance. If there is no excitation, all we're going to see is just that resistance, right? Our Thevenin equivalent circuit would literally just be a resistor in series with a short circuit because there's no Thevenin voltage to deal with, okay? So if I were to redraw things, when I look in through my input terminals, I'm going to see what's commonly known as the input resistance of the amplifier, right? And now I'm going to essentially kind of reconnect my source side. So here's RS. Here's V sig, like so. And here is the actual input voltage Vn of t that's applied across the input terminals of my amplifier. So that input resistance Rn sees that whole voltage, whatever it may be, okay? Now, let's say that I disconnected my load while leaving my signal on and looked in through the output terminals. What should I see? Well, I should see a true Thevenin equivalent circuit, a voltage source in series with some resistance, okay? So I'm going to draw that part over here. So the resistance that we would see looking into the output terminals is unimaginatively going to be called the output resistance of our amplifier. And it's going to be in series with a voltage source. Now, in circuits 1, we always had an independent voltage source. But we're expecting our device, because it's an amplifier, to be able to scale that input signal to generate some different output signal. So I'm going to choose to use a dependent source here in my Thevenin equivalent circuit to take into account that scaling that we expect to see because we've got an amplifier, okay? So I'm going to have right here my voltage gain A. times my input signal Vn of t. I'm worried that this is going to run into my terminal, so I'm actually going to scooch this over a little bit just so that it doesn't overlap things too much. Sorry about erasing and redrawing this. So AV times Vn of t like so. And then across here, we would have the output voltage of our amplifier, and then reconnecting my load RL. And here is my load voltage VL of t like so. So everything inside this purple box that I'm outlining is what we're going to call the practical voltage amplifier model. Okay. Generally speaking, the input resistance R in, the output resistance R out, and the voltage gains of our amplifier would all be information that's included in the data sheet for the whatever amplifier that we happen to purchase to use in our system. So all three of those pieces of information about the behavior of the amplifier should be readily available for any amplifier that you go out and buy. Okay, so that's why it's the practical amplifier model, because it's incorporating the practical results of test measurements to consider input resistance, output resistance, and practical voltage gain. Okay. Any type of amplifier can be quantified by those three parameters: the input resistance, the output resistance, and the gain of the system. Okay. So an operational amplifier, and we're moving on from here, is just a special type of voltage amplifier. I say it's a special type of voltage amplifier because it's what's called a single-ended output differential amplifier, meaning that it has multiple input signals, right? We talked about it having a non-inverting input terminal and an inverting input terminal back in circuits 1, but it only has a single output terminal. So that's why it's a single-ended output differential amplifier. So we actually have to very slightly modify our practical voltage amplifier to work for op amps because we have multiple input signals, okay? So let's talk here, let's call this operational amplifiers. And our practical model for our op amp is going to look something like this. So here's our input resistance, okay? I am going to arbitrarily assign this top terminal here to be the non-inverting input that we call V plus back in circuits 1, and this bottom terminal here to be V minus, which is corresponding to our inverting input terminal that we were dealing with back in circuits 1. So instead of that input resistance being between essentially the input and ground, now it's the resistance seen between the inverting input and the non-inverting input, okay? And we're no longer going to call the voltage drop across that input resistance V in, we're going to call it a differential voltage because it is the difference between those two node points in our system. So this is going to be our differential voltage VD, like so. And our differential voltage will always be defined such that the positive polarity terminal of VD is on the same side as our non-inverting input, and the negative polarity terminal of VD is on the same side as our inverting input. Okay, so that's the input side of the amplifier. Then over here on the right, I'm going to deal with the output side of our model. So this is that dependent source. I'm going to give this guy a name, AVOL. Okay. So this is what's called the open loop voltage gain of our amplifier. This is something that is available on our data sheet, things like that. Okay. And then that's going to be in series with the output resistance R out like so. And then I'm going to put a common ground bus across this whole guy, like so. And then this voltage measured between the output terminal and ground is what gives us our output voltage for our op amp. So this is our practical op amp model. And in circuits 1, we kind of represented this with that triangular model where we had our non-inverting input voltage V plus on the terminal with the plus sign, our inverting input terminal voltage V minus on the terminal with connected to the minus sign, and then our output voltage was on the right. So essentially, until we learn better, anytime we see this in a schematic diagram, we are going to replace it with that practical model so that we can do a more formal analysis of exactly what's going on. Now, there are limitations to what this model can do. And so we are going to talk about what those limitations are with an example. So let's say that we have the following circuit. So I'm going to ground my inverting input terminal. I'm going to put a 1-volt DC source between my non-inverting input terminal and ground. And then I'm going to measure the output voltage of this particular op amp. Now, as we talked about at the very beginning of class, amplifiers are active devices, meaning that they require external power. So I'm going to make a note of that by adding a positive supply voltage terminal here, which I'm going to say is 10 volts, and a negative supply voltage here, which is negative 10 volts, right? So that's us applying power to this device. And let's say that the open loop voltage gain for this amplifier is 100,000 volts per volt, okay? That is actually not particularly good for a well-designed operational amplifier. Well-designed op amp can have one that's meant specifically for providing voltage gain, can have voltage gains of a couple of million pretty regularly. So 100,000 is average at best. Okay. Our input resistance is going to be 1 mega ohm. This is a fairly typical value for a bipolar junction transistor based op amp circuit. If it were a MOSFET based op amp, this value would actually probably be closer to 1 tera ohm, or 1 times 10 to the 12 ohms, because of how MOSFET transistors are actually constructed. Okay, so 1 mega ohm is a pretty reasonable value for a BJT based op amp. And then lastly, our output resistance, R out, is going to be 25 ohms. This is actually a bit higher than you would see the output resistance of a well-designed op amp. It would typically be in the single-digit ohms, or actually in the milliohm range for a well-designed op amp. So this is a pretty middling or average op amp, like you would get if you went and bought a general purpose op amp like a TI UA 741 op amp, which is actually the most commonly used op amp in existence. Okay, which is where those numbers came from, for what it's worth. Okay, so what I want us to do first is we're going to learn how to take this schematic diagram representation and then plug that into our practical op amp model so that we can analyze the circuit. So how I usually do this is I start by just drawing my practical op amp model by itself over here. So we were told that our input resistance was 1 mega ohm. So I'm just going to label this resistor as being a 1 mega ohm resistor. Here is my dependent voltage source. So 100,000, I'm not going to write it like that. I think that's the same thing as 10 to the 5, right? So that'll be a little bit more succinct. So I'm going to put 10 to the 5 times VD, where this will be VD, which makes this my non-inverting input terminal, and this guy over here is my inverting input terminal. Then I've got my output resistance of 25 ohms. And here's my common ground bus, right? And for what it's worth, here's the output voltage that we're looking for. So because in my schematic diagram on the left, I didn't include any load resistance or anything like that, we should have an open circuit between the output terminal and ground in our practical op amp model. If I had included some load resistance, we would just put the load resistor between those two terminals like that. Okay. So my inverting input terminal is connected directly to ground. So I'm literally just going to connect that node to ground like so. And then I have a 1 volt source between my non-inverting input terminal and ground. So I'm just going to put that over here as a 1 volt source like so. So before we perform our circuit analysis here, Does anybody have any questions about how I redrew our circuit using the practical op-amp model? So for what it's worth, when I do this, I always just start with the practical op-amp model itself and then make all of the external connections. When we get into particularly negative feedback circuits, I might actually flip that input resistance over, putting the inverting input terminal on top, just because it's slightly easier for me to draw the feedback connections that way. Doesn't change anything as long as we remember to always put the positive polarity terminal of VD on the non-inverting input side and the negative polarity terminal of VD on the inverting input side. Nikolai?
So for the impulse that we supply, do we have to include this in this diagram as well?
So fantastic question. There is nowhere in this diagram, there is nowhere on the practical op-amp model for us to include our supply voltages. We just have input resistance, output resistance, and gain. And so what we're going to see here in a moment is when we use this model and don't take into account our supply voltages, we're actually going to see unrealistic results, okay? So let's perform our circuit analysis. And we're just going to do this really quickly, okay? So by inspection, I believe that you guys should be able to tell me what my differential voltage for this circuit is. So anybody have any thoughts on what that might be? Yes, sir.
1 volt.
1 volt, absolutely right. Since our inverting input terminal is grounded out, the voltage drop across our 1 mega ohm resistor is literally just the 1 volt that we have applied. Great job. Our output voltage in this case, so because we don't have any load resistance, there's going to be no voltage drop across our 25 ohm resistor. There can't be any current flowing through it. So our output voltage is literally just going to be 10 to the 5 times VD. So that would be 100,000 volts, according to the practical op-amp model. Is that realistic? Good God, no. Right. There is no way in hell, if I put 1 volt across the input terminals of an op-amp, it would give me 100,000 volts at the output. So the problem with our model, particularly in the open loop case, is that it does not include what are called the effects of saturation distortion, okay? So I'm going to put a big X there saying, no way in hell that's ever practically happening. And now we're going to talk about what saturation distortion is. So how many, if any of you, have heard of the term saturation in the context of electricity, electronics, and things like that? Nobody? Okay. Well, it's something that we're going to talk about over and over and over again in this class, in your electronics classes, and things like that. Essentially, what saturation boils down to in the context of electrical engineering is if you have a system and a change in the input no longer causes a change in the output, the system is referred to as saturated, okay? We can't cause any more change in the output due to a change in the input, okay? So saturation distortion is something that occurs in op-amps, and put simply, in a real op-amp, the output voltage cannot exceed the power supply voltages. And I'm going to give us a mathematical definition here in just a second. So I want to add a couple of comments to this. So what I mean by it cannot exceed the power supply voltages is the output will never be more positive than the positive supply voltage, and it will be never be more negative than the negative supply voltages. So those supply voltages represent the absolute maximum positive value and absolute maximum negative value that you could ever see. Now, technically, that is only true for what are called rail-to-rail op-amps that are designed to work all the way up to the positive power supply voltage and all the way down to the negative power supply voltage. Most op-amps aren't actually rail-to-rail op-amps. So there's about, depending on the design, between 1 volt and half a volt of effectively dead zone when you get up close to the power supply voltages. So you might have, for this case, your output voltage could never be larger than, let's say, 9.5 volts, and your it could never be more negative than, say, negative 9.5 volts or so. Typically, when you buy an op-amp on the data sheet, it will tell you whether or not it is a rail-to-rail op-amp, or it will just explicitly state what the maximum largest output voltage it can generate is, or the maximum negative output voltage it can generate. So those are going to be known quantities, okay? So for this particular amplifier that we have, assuming it is a rail-to-rail op-amp, and we're going to assume rail-to-rail op-amps for everything we're dealing with in this class, just because it makes the math easier. What would the output voltage actually be? 10 volts, because our positive supply voltage is 10 volts. Absolutely right. So, generically speaking, for this class, we are going to say that our output voltage is going to be what I'm going to call VCC plus. This is our symbol for our positive supply voltage. And our output voltage will be VCC plus whenever our open loop gain times our differential voltage VD is greater than or equal to VCC plus. And for what it's worth, this condition is called positive saturation, because we're saturating to the positive supply voltage. On the flip side of things, and just to be clear, I'm going to put something here in the middle in a moment, so make sure you leave space as you're taking down these notes. Our output voltage is going to be VCC minus when AVOL times VD is less than or equal to VCC minus. This is negative saturation. And then in the middle, our output voltage is going to be actually AVOL times VD when VCC minus is less than AVOL times VD is less than VCC plus. And this is what's called our linear operation. For what it's worth, the reason why this is called linear operational mode is because this is the only range in which our operational amplifier behaves as a linear circuit element, in as much as the output signal is proportional to the input signal. So let's talk very briefly about linear range. Okay. So this is effectively a side effect of saturation distortion, so it's going to be still in this part of the notes. So the linear range for an amplifier is literally the values of the input voltage that can be amplified without hitting saturation, okay? So generically speaking, this is going to look like VCC minus divided by the open loop voltage gain will be less than our differential voltage, which is playing the role of our input voltage for these op amps, will be less than VCC plus over our open loop voltage gain. So this is how we're going to define our linear range, because VCC minus represents our maximum negative output voltage. VCC plus represents our maximum positive output voltage, and AVOL is what's converting our input to our output. This is how we arrived at this relationship. So I want us to very briefly plug in our numbers here and see what the linear range of our amplifier would actually be. So VCC minus, if my memory serves me correctly, was negative 10 volts, right? AVOL was 10 to the 5 volts per volt. So it doesn't have dimension, so I'm just going to leave that off. Then we're going to have less than VD is less than positive 10 volts over a factor of 10 to the 5. What's 10 over 10 to the 5? 1 over 10 to the 4th, sure, okay. Put that in a voltage, it's going to be 100 microvolts, right? So our linear range for this particular amplifier in an open loop configuration, that's rather important, is going to be 100 microvolts is less than VD is less than positive 100 microvolts. So our linear range here is incredibly small, okay? So this is a large part of the reason why the op-amp circuits that we were dealing with back in Engineering 221 all had negative feedback. In a few days, when we talk specifically about the properties of negative feedback, one of the main advantages is an increased linear range, because negative feedback tends to lower the voltage gain of the system, right? So with a couple of well-chosen resistors, we can lower that open loop voltage gain of 100,000 or so down to something that's much more manageable and predictable using negative feedback. Just for what it's worth, because this is, I guess, kind of a common misconception or something here. So I chose to use 100,000 volts per volt as the open loop voltage gain for an op amp. That is literally coming from the data sheet as a typical value, but you would be hard pressed to find an actual op amp whose open loop voltage gain is consistent from one produced device to the next, just because of small manufacturing errors in the microfabrication process. So the 100,000 volts per volt is actually an average value over an entire production run. You might see some with open loop voltage gains as low as 20,000 volts per volt and some as high as 2 million volts per volt for the same exact amplifier, just depending on how that fabrication process went. So another very important reason why feedback is used in op-amp circuits is to make the gain consistent, because it can vary so much from unit to unit in an open loop configuration. All right, that is enough out of me for today. So what we're going to talk about in our class meeting on Monday is a few specific applications of open loop amplifiers like we've kind of talked about today. We're gonna actually do a couple of little simple design projects on Monday, showing us how we can think about things and how to use these systems. I am going to be posting a homework assignment related to just this material. I think it's like 2 problems or something this afternoon, and it'll be due next Wednesday. If you have any questions or anything, I would be more than happy to answer them. I did make sure that it's actually recording today, so I will have the lecture video as well as these notes up probably by 7 a.m. tomorrow at the latest.